This is Mr. Hassan's Maths channel, and I'm now answering question number 6 from the February-March 2020 International A-Level Paper 4 Mechanics paper from Cambridge 9709. This is the paper which is for variant 2, February-March. Now, in this question here, we're told that on a straight horizontal test track, driverless vehicles with no passengers are being tested. A car of mass 1,600 kilograms is towing a trailer of mass 700 kilograms along the track. The brakes are applied, resulting in a deceleration of 12 meters per second squared. The braking force acts on the car only. In addition to the braking force, there are constant resistive forces of 600 newtons on the car and 200 newtons on the trailer. Find the magnitude of the force in the tow bar. Okay, so you have a tow bar, which is towing these, which is, connecting these two particles. Okay, so you have basically a car. Okay, I'll just draw it like a block, and it's towing a trailer. Okay, and they're connected with a tow bar. They're connected together with a tow bar. Okay, and we have a certain situation here where the car has a mass of 1,600 kilograms, and the trailer has a mass of 700 kilograms. Okay, let me just put that a bit bigger so I can write in it. So that's 700 kilograms, the mass of the trailer. Okay, so you have here resistive forces acting on the trailer and the car. All right, so you have a resistive force on the trailer and a resistive force on the car. On the car, the resistive force is 600 newtons. And on the trailer, the resistive force is 200 newtons. Okay, now I'm going to just try to make you understand what the difference is between a rope and a tow bar and a bar. Okay, so if the car and the trailer were connected with a rope, okay, and let's just say there was no braking force for now. Just say the car had a driving force that was pulling it forward. Okay, so in the case that there's a rope or a tow bar, the same situation would be occurring, that the trailer is being pulled along by the car and the car is slowed down by the trailer. So you'd have a tension in the string or the rope or the tow bar, okay, and this will be the direction. In terms of, if you consider the trailer, then the tension, if you consider the force acting on it from the rope, it will act towards the right, towards the way that it is moving. Okay, but if you consider the car, which is pulling the trailer with this driving force, then the tension in the rope or the tow bar, whatever it is, will be acting in the direction to slow it down. So we're acting against the direction of motion. So that's how the tension would be in the string or in the rope or the tow bar. Okay, if you consider the car separately, if you consider the trailer separately, that's how that would be. Now, what's happened in this situation is the brakes are applied. So of course, when you apply the brakes, you take off your foot from the accelerator and you press the brakes, unless you don't know how to drive, right? So you take your foot off the accelerator, so the driving force stops. No more driving force, but there is a braking force when you put your foot on the brakes, which also acts in this direction. Okay, now when that happens, this tension is no longer there. And there is now another force there that is going to be acting. Okay, and that force is going to be what's called the thrust. Because now basically, if this was a rope, then you put the brakes on. This would continue moving. Okay, the brakes only applied to the car. This would continue moving and it would smash into the car, right? If it was just a rope. But a tow bar is a rigid object. It doesn't bend, nor does it buckle, right? So when the brake is applied, then what stops the car and the trailer from colliding? Well, the thrust in the tow bar, which now acts in the opposite direction, keeping them apart from each other. So the tension becomes now a thrust Okay, well, I'll still call it T. That's the force in the tow bar, keeping them apart from each other now. Okay, so this is the situation that we have here. The brake has been applied. That means the driving force has stopped. And when this happened, they told us the deceleration, so it's still moving in this direction, but the acceleration is negative 12 meters per second squared. So it's decelerating, so acceleration is negative 12 meters per second squared. Okay, so this is the situation that we now have in this, kind of system. So that deceleration is for the whole system. Okay, so this and this, they're both decelerating with the same deceleration. So now they're telling us to find the magnitude of the force in the tow bar. All right, so if you want to find the magnitude of the force in the tow bar, okay, then we have a couple of options. We could, what we could do in this situation is we could do the following. First of all, okay, we want to find the tension in the tow rope. So what we could do is we could consider one of the particles by themselves in isolation from the others. So for example, if I consider this particle by itself, I have a problem because I have two unknowns. I know the acceleration is minus 12. The acceleration of the whole system is the same. I know it's negative 12 meters per second squared, but I have two things I don't know. One is the braking force and the other one is the thrust acting on this. Okay, so those are two things that I don't know in this situation, right? So I can't really isolate this on its own and find the force in the tow bar, the thrust. However, if I consider this particle by itself, I know that its acceleration, as it's one particle moving, it's like one system moving with the same deceleration. If I consider this by itself, then I know all the forces acting on it except for the thrust, and I can find the thrust. So that's probably the easiest way to deal with this situation in this particular case. So I'm going to now just focus alone on the trailer, and I'm going to, it's as if I'm ignoring what's happening over here, but it's not really ignoring it because what's happening in this part of the system affects the thrust. If, for example, the mass was different, if the braking force was different, if the resistance was different here, that would affect the value of the thrust. So you're not really ignoring it, but you're just isolating one part of it, so we can just focus on the forces acting on that particle alone. So we're going to consider the trailer alone. So we're going to consider the trailer on its own. So consider the trailer alone. Okay, if we consider the trailer alone, then we can see what forces are acting on the trailer alone. And they are basically, it's moving in this direction. So I'm going to use the resultant force. And now if it's moving in this direction, everything else, these two forces are both acting towards the left. So I've got negative T. Okay, negative T and minus 200 is equal to its mass, which is 700, times the acceleration, which is negative 12. Okay, we're using resultant force equals the mass times the acceleration. This is the resultant force. This is the mass times the acceleration. And then we should be able to find what T is. You have 7 times 12, which is 84. So that's 8,400 minus 200 equals T. Okay, so we can say T is equal to 8,200 newtons. And there's the answer to part A. Okay, we could have found the braking force first here, and then we could have used this if we wanted to. We could have found the braking force by doing what I'm going to do now. Okay, but it's like you're answering part B first anyway. So I'm going to show you how we can find the braking force by using just this part of the system. Okay, now that we have the tension. All right, we can also find the braking force by considering the whole system as one. In fact, I'm going to show you how to do it in two ways. One way is by considering the whole system. One way is by just considering what's happening in this part of the system. Okay, so let's consider, in fact, I'll take this whole thing. Oops, what am I doing? I'll take all of this, copy it, and I'll paste it down here. Okay, I'll just put it above. Okay, so we got all of this. All right, we want to find the braking force. So I'll put it over here so it's in the right place. Okay, so we're going to find the braking force now for this. Let's move this up here. Okay, So, as I said, we can do it in two ways. I'll show you two ways. So let's look at the first method. Okay, method one is where we could just basically just consider what's happening here. Right, just change our focus to what's happening with the car. Now we know the tension now is 8,200 newtons. We know that now. So that's the tension or the thrust, sorry, not the tension, the thrust in the rod. Okay, so if we consider what's happening here, we know that this whole system is moving with this same acceleration, 12 meters per second squared, or deceleration, of 12 meters per second squared. And we know that it's moving towards what we've drawn as a right. So I'm going to draw the forces acting. So I've got the thrust in the rod is acting in the same direction as the movement, keeping these two apart. Then you've got minus 600 and minus B. Okay. And we know the thrust is basically 8,200. This is 8,200. That's the thrust. Okay, 8,200 minus 600 minus B. That's the resultant force acting on this. And that's equal to the mass, which is 1,600, times acceleration, which is negative 12. As you can see, the only thing we don't know now is B. So we can say B is equal to, that's 8,200 minus 600, that's 7,600. I'm going to have plus 12 times 16. Okay, let me get the calculator out. 12 times 16. That gives you 192. So plus 192. So 19,200. With two zeros. So B is going to be equal to, you add them together, 19,200 plus 7,600. Whoops. 19,200 plus 7,600. That's 26,800. 26,800 newtons. Okay, so that's one way of doing that, answering the question, by considering just the car. Okay, another way we could have done it actually is by considering this as just one block moving. Consider the whole thing as one kind of particle, the whole system as one particle. So you'd have the combined masses, which is 23,000 or 2,300 kilograms. 700 plus 1,600, that's 2,300. So 2,300 kilograms. And you have the combined resistive forces acting in this direction, which would be 200 plus 600. That's going to be 800. Okay. And you have the braking force, you have the thrust acting. Okay. Well, the thrust now, when you take it as one whole system, you don't have to consider the thrust. Okay. That's inside the system. Right. So there's, between them, the thrust, we don't have to even think about it, but we do have the braking force, okay, which is B, which is going to be considered acting on the whole system because it's all moving together. All right. So that braking force is what we don't know. So basically now we know that the whole system is decelerating for minus 12 meters per second squared. So we can say the resultant force, if we take again this side as positive, is negative 800 minus B equals the mass 2,300 times acceleration negative 12. So B is going to be equal to basically 2,300 times negative 12 minus 800. Okay, so what does that give us? 2,300 times negative 12. Okay, that gives us negative 27,600. So it's going to be positive when you move it to this side. So it'll be 27,600 minus 800. Okay, so when you work that out, so that becomes positive. All right, minus 800, and it gives us 26,800, exactly the same answer, 26,800 newtons. So it doesn't matter which way you do it, both of the ways are perfectly fine. All right, as you can see, we get the same answer. I just want to show you a variety of ways of answering such questions. Sometimes you have to consider the system as a whole. For example, if you can't find the thrust in the system. Here, they gave us acceleration, so we could find the thrust in the system. But if you didn't have the acceleration, okay, then you could find the acceleration by ignoring the thrust by taking it as one particle. Okay, then you don't have to calculate the thrust to find the acceleration. And once you've got the acceleration, then you can calculate the thrust. So there's different ways that you can deal with such questions depending on what you've given you. So here we took the trailer alone because we couldn't look at the car alone because there's two unknowns. All right, so the trailer alone, we could find the answer. And then we had an option. Either we take the trailer alone, okay, sorry, the car alone, now we got the thrust. We could find the braking force then, or we can take the whole thing as one system, and the only thing we don't know is the braking force then. Okay, so both of those ways are perfectly valid to answer the question. Okay, so there's the answer for part A and part B. Okay, very important question actually, this one. It's got a lot of things that are very important for us to understand about dynamics. Okay, now, part C. At the instant when the brakes are applied, the car has a speed of 22 meters per second. At this instant, the car is 17.5 meters away from a stationary van, which is directly in front of the car. Show that the car hits the van at a speed of 8 meters per second. Okay, so you have your car and your, the whole system, the trailer and the car together. I'll just take it as one whole system now. Okay, the car and trailer, which was 2,300 kilograms, 1,600 plus 700. Okay, so that's one system, the car and the trailer. Okay, it's decelerating still. Okay, it's decelerating at negative 12 or 12 meters. You can say 12 meters per second squared is the deceleration. Okay, and there is a van which is stationary. Okay, we don't know anything about the van right now, but we know that the distance between the trailer and the van is 12.5 or 17.5 meters. That distance is 17.5 meters. Okay, so now it's traveling at a speed of 22 meters per second at this stage. And here we have to show that the speed is 8. So we're not going to put 8 here, we have to show that the speed is 8. All right, so here I think it's a classic example of using the suvat equations. Okay, so if you write down what we know, constant acceleration. Okay, we know that it's going to move 17.5 meters. We know that its speed initially was 22 meters per second. We know that its speed at the end we have to find. The acceleration is negative 12, and the time we don't know. Okay, and we don't really need because we can use one of the equations of motion as we see if you're doing Cambridge in the formula sheet. V squared equals u squared plus 2as. We want to have s, u, and a we have been given, and v we have to find. So we have to use these four. So we're going to use v squared equals u squared plus 2as, that found on the formula sheet. So v, as we said, is what we have to find. So v squared equals u squared. So u is 22, so that's 22 squared plus 2 times a, which is negative 12, times s, which is 17.5 meters. Okay, so now we can work out what this is, and hopefully it will give us the answer that we need. So we have 22 squared plus 2 times negative 12, okay, times 17.5. So hopefully this comes out as 64 because it has to be 8. That's right, good. So v squared is equal to 64. Therefore, v is equal to 8, okay, meters per second. So there we have the speed. Okay, now the speed is 8 meters per second. We really should say plus or minus 8 meters per second, but we only consider the positive speed. Okay, we're not considering that it's gone further and then come back because it's still decelerating and then come back to here again. Okay, because what would happen if it continued decelerating? It would eventually come to rest if the van wasn't there. Okay, it would come to rest and then it would come back again. So the negative 8 meters per second is kind of referring to the speed it would be going if it was coming back again. If it can continue decelerating, it's like when you throw something in the air, it decelerates, it comes to zero, it's still decelerating, and it's still decelerating, it's coming down to ground again. Okay, so anyway, 8 meters per second. 8 meters per second is the velocity or the speed when it reaches just before it collides with the van. Okay, so there's the answer to part C. We've shown that's true. Then it says part D. After the collision, the van starts to move with a speed of 5 meters per second, and the car and trailer continue moving in the same direction with a speed of 2 meters per second. Find the mass of the van. So here we have a question about the conservation of linear momentum. Okay, this is a question, and I'm going to save this video in part also in the playlist for momentum, because this last part of the question is dealing with that. Okay, so we have to find the mass of the van. So we have the car and the trailer together, which have a mass of 2,300 kilograms. We have the van with a mass we're going to call M. We don't know what it is. Okay, so we have the situation before and we have the situation after. Before the collision, this is moving at 8 meters per second at the point where they collide. Before the collision, this is stationary, as it said. The van is not moving. Okay, a stationary van. And then we're going to think about the situation after the collision. We're going to have this moving with a speed of 2 meters per second in the same direction. And we're going to have the van, of course, will move in this direction at a speed of 5 meters per second. So we've got to find the mass of the van, so we can use the conservation of linear momentum. The momentum before the collision and after the collision will be exactly the same. So if I take the situation before the collision, I've got the mass of the car and trailer, which is 2,300. So 2,300 times the velocities, that's before, okay, for the car and trailer. And for the van, it's going to be the mass times 0. That's before the collision. After the collision, you're going to have 2,300 times 2, okay, plus, and you're going to have m times 5. Now, we've taken this side as positive, obviously, and, you know, all the movement is in this direction, so we don't have to worry about any negative signs here. If something had changed direction, then we would have to assign it a negative velocity if we took this side as positive. So that's where you have to be careful. In this case, we don't have that issue. Everything's moving in one direction, okay, before and after the collision. All right, so now this becomes 0, obviously. So we end up with 5m. Basically, we're going to have 2,300 times 8 minus 2,300 times 2, okay, divided by 5. Okay, so so that's 2,300 times 8 minus 2,300 times 2 divided by 5, and that will be what we're trying to find. Okay, so let's figure that out. So we have here 2,300 times 8 minus 2,300 times 2, all of that divided by 5. That gives us 2,760 kilograms. So the mass of the van is 2,760 kg. All right, so there's the answer to part D of this question. Okay, so I hope that was clear. All right, and hope you understood. So that completes this question. So part D of this question is all about the conservation of linear momentum, and part C is all about suvat equations, constant acceleration. Part A and B are about dynamics. So it's a bit of a mixed question, lots of different things in there, but I hope that was clear. Okay, other questions from this particular paper can be found in the playlist that will appear at the top right of the screen at the end of this video. Other questions from this particular, well, I guess from the topic of dynamics, you'll find in this playlist over here. From the topic of suvat equation, suvat, you'll find in this playlist. And in fact, what I'll do is I'll put the playlist here for momentum. Okay, and here you will find the playlist for the for suvat. So yes, suvat and momentum, you'll find the playlist in these places here. So that completes this question. As I said, thank you for watching and see you soon.